All right, let's talk about something fascinating. How do you detect something you can't even see? Today, we're diving into a piece of tech that so many of us rely on for our safety, but we almost never think about it. I'm talking about the semiconductor gas sensor. We're going to pull back the curtain and see exactly how this tiny device smells dangerous gases that are completely invisible. You've probably seen one of these before, right? Maybe it's tucked away inside a smoke detector or a carbon monoxide alarm in your house. It's basically an invisible shield, a silent guardian. But have you ever really stopped and wondered how it actually works? I mean, how does this little piece of metal and ceramic detect something it can't see? Well, that's the awesome question we're going to answer as we zoom right in. So at its very core, a sensor like this one, this is an MQ6 model, it has one really critical job: to sniff out specific gases. We're talking about things like liquefied petroleum gas, or LPG, and other stuff that can combust. It does this by just constantly monitoring the air, just waiting for the tiniest change that could signal danger. Now, this is the secret sauce right here. The sensor doesn't smell like our noses do, not at all. Instead, the entire way it works hinges on a basic electrical principle. When a target gas floats by, the sensor's internal electrical resistance literally changes, and it's that precise, measurable drop in resistance that sounds the alarm. To really get this, we've got to pop the hood and see what's inside. So let's break this amazing little gadget down and look at its key parts. What's just incredible here is how much engineering is packed into such a tiny space. On the left, you can see the whole thing put together. You've got the protective cap, the main body, and then right there in the middle, that's the heart of the whole operation, the sensing element. And see that tiny black square on the right? That's it. That's the microscopic stage where all the magic happens. So if we simplify it, it really boils down to three main parts. First up, you've got the filter. That's the stainless steel mesh cap that lets gas molecules in but keeps junk like dust and water out. Second, you have the nose. This is the sensing element itself, a little ceramic tube coated in a special metal oxide, usually tin dioxide. And third, the heater, which is a tiny coil tucked inside that is absolutely essential to making the nose do its job. Okay, so we've seen the parts. Now for the main event. How do chemistry and electricity actually team up in this tiny space to detect a gas that you can't even see? Before we go any deeper, let's make sure we're all on the same page with this idea of electrical resistance. The absolute best way to picture it is like traffic on a highway. Seriously, when resistance is high, it's a massive traffic jam. There are roadblocks everywhere, and very few cars, or in our case, electrons, can squeeze through. When resistance is low, that highway is wide open and traffic is just flowing freely. So picture this. In normal, everyday clean air, oxygen molecules are constantly sticking to the surface of that tin dioxide sensor. These oxygen molecules, they're a bit greedy. They snatch up free electrons from the sensor material, effectively pulling them out of the flow. This creates our roadblocks, which means high electrical resistance. It's basically a permanent traffic jam. But then, a target gas, like LPG, drifts into the sensor. The second it hits that heated surface, it reacts with those oxygen roadblocks. This chemical reaction happens super fast, and it basically knocks out the oxygen, forcing it to release those electrons it was holding onto. And just like that, the roadblocks are gone. And this just lays it all out perfectly. It's such an elegant process. In clean air, you've got a constant traffic jam. That's high resistance. The moment the target gas shows up, boom, the road is clear and traffic starts flowing. That's low resistance. The sensor's circuitry is built to do just one thing. Notice that sudden drop from high to low resistance. And when it does, it knows the gas is there. Now, remember that little internal heater we mentioned? This is where it becomes the unsung hero of the whole story. For this whole gas and oxygen reaction to happen, the sensor's surface needs to be incredibly hot. We're talking up to 400 degrees Celsius. That is way hotter than most home ovens ever get. Without that intense, focused heat, the chemical reaction would be way too slow to be useful, and the sensor just, it wouldn't work. So we've just seen how this sensor brilliantly plays with chemistry and electricity on this tiny, superheated surface. It's amazing stuff. Now let's zoom back out and talk about why this clever little piece of engineering is so important in our world. The real genius of this tech comes down to two things. One, it's incredibly sensitive to even tiny amounts of gas. And two, it's relatively cheap to make. That combination makes it perfect for all sorts of uses. In our homes, it's a lifesaver, detecting a gas leak from a stove long before it becomes a real danger. And on a bigger scale, these things are the front line of defense in industrial plants, and they're even used to track citywide air quality, giving us a real-time picture of the air we breathe. So the next time you happen to see one of these little gadgets, you'll know the incredible science that's packed inside. That tiny heated surface, creating and clearing electron traffic jams, all to protect us from dangers we can't even see. It's a powerful reminder that there's this whole world of invisible forces all around us. And it makes you wonder, if we can build a device to see this invisible thread, what else is out there that we should be looking for?